Hello, Earth Scientists. I wanted to walk you guys through some radiometric dating practice problems. Feel free to watch this after you attempt these questions yourself if you would like to get a true assessment of where you're at. And then maybe watch this after so you can get an explanation of where you need some support. So we're going to start with talking about these diagrams here. Here we have information in this image here about the half-life of these isotopes, depending on which isotope you're using to date your sample. So the half-life time is important to reference there. And then this is our decay of radioactive material shown as a graph. So depending on how many half-lives have occurred, we can use this. Usually you're going to read it from the y-axis and then down to the x-axis. So if you see that 50% of your sample remains, that would intersect with our curve here, and you would see that one half-life has occurred. If you see that only 25% of your sample remains, you would see that intersects here, and then you would say that's approximately 2 half-lives. So use both of these throughout all of the problems. Let's get started with number 2. If a sample contains 100 grams of a radioactive isotope, how much would be left after 3 half-lives? So we know with each half-life, half of the sample undergoes that radioactive decay. And there are a number of ways in which you can solve these types of problems. I'm going to write out just dividing by 2 every single time. So over the course of one half-life, half of our material undergoes radioactive decay. So if I divide it by 2 one time, I know that 50 grams would be left after one half-life. But it's saying 3 half-lives, so I need to divide this number by 2 more times. So I'm going to do 50 grams divided by 2, and that's going to give me 25 grams remaining after that second half-life. And then if I divide this again, 25 grams divided by 2, that would be approximately 12.5 grams, and that would be after the third half-life. So this would be our final answer. Our best choice would be D down here. Let's try number 3. Oh, it looks like the numbers here are a little different. It looks like this matches up with number 2 on your form. So this problem is saying if a sample contains 50 grams of a radioactive isotope, how much would be left after 2 half-lives? So we're going to set it up in a similar way. Let's write out how much we have to begin with, 50 grams, and we're going to divide it by 2 to show how much remains after one half-life. And this is saying how much remains after 2 half-lives. So let's divide this number by 2 one more time. That is what remains after 2 half-lives. So our best answer would be 12.5 grams. Let's try number 3 here. If a sample contains 20 grams of an isotope that has a half-life of 1,000 years, how much would be left after 2,000 years? So this problem gives us information in a different format. We know the half-life time it takes for it to undergo one half-life is 1,000 years. And this is saying after 2,000 years, how much would remain? So we know that every 1,000 years, that's a half-life. So this would be one half-life, the second half-life. And if we're starting with 20 grams, it looks like we have to divide this number by 2 twice. So we're going to set up 20 grams divided by 2 would give us 10 grams remain after one half-life, after 1,000 years. This is asking us after 2,000 years or 2 half-lives. We need to divide this by 2 again. to get our answer of 5 grams. Great job. Let's try number 4. If a sample has only 20 grams remaining after 3 half-lives, how much was there to start with? So we could set up this problem and work backwards. We know that 3 half-lives have occurred, and we end up with 20 grams after these 3 half-lives. Third half-life. Let's write that differently. So in order to get 20 grams, we're going to need to multiply this by 2 to get what we had originally. So we're going to say this needs to be multiplied by 2. And that's going to give us 40 grams. And that is what should remain after the second half-life. So we're going to take 40 grams and multiply it by 2 to get the 80 grams. That is what remained after the first half-life. So 80 grams times 2 would be 160 grams. And there are numerous ways in which you guys can set up the math involved for these types of problems. And if this way works for you, great. If a different way works for you, also awesome. So our final answer is going to be 160 grams to start with. Great job. Let's do number 5. If you start with 1,000 grams of carbon-14, how much would remain after 4 half-lives? Awesome. So we're given the original quantity, 1,000 grams, and we're going to divide this out by 2 a couple of times to see how much remains. So that's how much remains after 1 half-life. We're going to divide it by 2 to figure out how much is left after the second half-life. So 500 divided by 2 would be 250 grams after 2 half-lives. We're going to divide it again to figure out how much would be left after 3 half-lives. Let's write our answer down here. So 125 grams remains after 3 half-lives. And then we're going to divide it one more time to figure out how much remains after 4 half-lives. So our answer would be 62.5 grams. Great job. Let's try number 6. Assume you start with 10,000 carbon-14 atoms. Which of the following would be true? After 2 half-lives, there would be 5,000 carbon-14 atoms. Well, we know that is not true because after 1 half-life, this 10,000 would reduce by half to 5,000 atoms. So we can get that one off of our options. After 1 half-life, there would be 250 carbon-14 atoms remaining. We know that's not true because it would be 5,000 remaining after 1 half-life. After 3 half-lives, there would be 2,500 carbons remaining. Well, we know this is after 1 half-life. If we have the sample undergo 2 half-lives, half of 5,000 would be 2,500. So we know that this isn't true because this quantity matches up with 2 half-lives. So this last one must be correct. Let's do the math in order to support this answer that after 4 half-lives, we have only 625 carbon atoms remain. So we have 5,000 atoms to start. divided by 2 would give us 2,500 atoms. So that's 1 half-life. Divided by 2 again would give us 1,250. And that's after 2 half-lives. Divided by 2 again would give us our 625 number of atoms. So this one must be correct. Great job. I'm going to make some space, so let's clear our drawings. And let's try number 7. What is the half-life of potassium 40? So let's go back and use the chart that is shown at the beginning of this form. So here is potassium. Potassium 40 will decay into argon, and the half-life is listed here, 1.3 billion years. So it takes 1.3 billion years for potassium 40 to undergo a half-life. Oh, here we are. So potassium 40 has a half-life of 1.3 billion years. Let's move on to number 8. If a fossil originally contained 100,000 potassium 40 atoms, and it now contains only 12,500, how old is the fossil? So the hint is figure out how many half-lives have passed, and then use the chart to calculate how old it is based off of the number of half-lives that have passed. So let's use these two numbers and figure out how many half-lives have passed. Let's write our work over here. So 10,000 divided by 2 would get us to 5,000. And that would be 1 half-life. Divided by 2 again would give us 2,500. Oh, sorry, I'm using the wrong quantities. Let's try that one again. So we start with 100,000 and we divide by 2 to get 50,000. And that is 1 half-life. 50,000 divided by 2 again would give us 25,000. And that happens after 2 half-lives. We're not quite at 12,500, so let's keep dividing. If this undergoes another half-life, we would end up with our quantity, 12,500, and that happens after 3 half-lives. Okay, so now that we know that 3 half-lives have passed, let's use the chart at the beginning of our form to figure out how old this sample must be. So if we know that 3 half-lives have passed and we're working with the potassium, again, potassium 40 has a half-life of 1.3 billion years, and that's only 1 half-life. So we need to multiply this half-life by 3. So let's go to our problem and see, we know 1 half-life is 1.3 billion years. And we need to multiply that by 3 to get how old the sample is. So 3 times 1.3 would be 3.9 billion years. And that would be our final answer, how old that sample is. Great job. Let's move on to number 9. And we're going to be using this diagram in order to answer the next couple questions. What is the half-life of the element in the picture? So here in this image, we have a sample that decreases by half over the course of time. So we are using this to figure out what's the half-life of this element. Do you see how long it takes for this original specimen to decay by half? It would happen over the course of this point to this point, which is 10 minutes. So our half-life, the time it takes for half of the sample to decay, would be 10 minutes. Let's move on to the next problem, which is number 10. If you start with 100 grams, how much do you have after 30 minutes? So we know that one half-life is 10 minutes. We just figured that out in the previous problem. So this is asking us how much is left after 30 minutes. So we know that it has to undergo 3 half-lives. So 30 minutes means 3 half-lives. So let's take our quantity and divide it by 2 3 times. So we would have 100 grams divided by 2 would give us 50 grams, and that's after 1 half-life. 50 divided by 2 again would give us 25 grams, and that's after 2 half-lives. And finally, divided by 2 would give us 12.5 grams, and that's after 3 half-lives. So our correct answer would be this last option, 12.5 grams. Great job. Let's do number 11. If you had 10 grams at 20 minutes, how much did you start with? So we know that this is still true. One half-life is 10 minutes. So this means if we're dealing with 20 minutes, this is 2 half-lives has passed. So let's work backwards and see what we started with. So 10 grams resulted after the second half-life. So we need to multiply this by 2 to figure out that we started with 20 grams at the beginning of the second half-life. We know that 20 grams remained at the end of the first half-life. Multiply it by 2 to figure out what we started with. So we started with 40 grams at the very beginning. So our correct answer would be 40 grams. Great job. Number 12, what percentage of the original carbon-14 remains in a sample after 11,460 years? So we're using the chart at the top to figure out how many half-lives have passed, and then we can determine the percentage from there. So let's hang on to this number, 11,460 years. So let's go back to the chart to learn more about carbon-14. Let's get rid of some of these drawings. Okay, so we know that carbon-14 is here, and a half-life for carbon-14 is this amount of time, 5,730. So let's bring this number to our problem and see how that relates to the number that was given. So we know a half-life, one half-life for carbon-14 would be 5,730 years. If we have this quantity given, we want to take this and divide it by this number in order to figure out how many half-lives occurred over this course of time. So let's divide 11,460 by the length of a single half-life, And go ahead and do this on your calculator. When you divide this out, you get the number 2. So this means that 2 half-lives have occurred. So if we know 2 half-lives have occurred, it's asking what percent remains from the original. Well, let's say we start with 100%. We divide it by 2 to figure out after 1 half-life, 50% remains, right? That's 1 half-life. But we are doing 2 half-lives, so we're going to take our 50% divided by 2 again to get 25% at the end of the second half-life. So our correct answer for number 12 must be 25%. Great job. A couple more, and then you guys are done. So number 13, how many half-lives have passed to yield a sample or produce a sample with 125 atoms of carbon-14 and 375 atoms of nitrogen-14? So the hint is we're going to figure out the percentage of the parent isotope remaining by dividing the number of parent isotopes atom over the total number of atoms. Then we're going to figure out how many half-lives from that percentage. Okay. So we have 125 of the carbon-14 and 375 of the nitrogen-14. So we know that carbon-14 decays into nitrogen-14. So let's add these up and figure out how many total atoms we're dealing with. Let's add 125 plus 375. So this means in total we're dealing with 500 atoms. And out of that 500, which of these quantities shows the number of atoms that have decayed? Well, we know we start with carbon and it decays into the nitrogen-14. So it's this quantity here that we want to compare for what decayed. So let's figure out what percent that is of our total. And we do that by taking our 375, dividing it by the total number of atoms, which is 500. And then we're going to multiply that by 100 in order to convert it into a percent. So on your calculator, do 375 divided by 500 and then multiply that by 100. You should get 75%. So 75% of this has decayed, which means 25% remains. So you could alternatively do this a different way and take a look at the amount that remains, which might be more helpful if we're using the graph. So we could also approach it and say 125 of the carbon atoms over the 500 total would give us our 25% of the remaining parent isotope. And I'd probably approach it this way as opposed to what we did earlier. Either way is fine, but you really want to focus in on the number of atoms remaining. And then let's use our chart. So let's go back to the top of the form. If 25% of the carbon remains, let's find where that lies on this y-axis. 25% would be right here. We would see it would intersect with our line there. So how many half-lives have passed? It looks like it intersects with our x-axis here. 2 half-lives have passed. So that means our correct answer is 2 half-lives. Remember to figure out the percent of the parent isotope that remains. Parent means what we start with, in this case, carbon-14. Great job, guys. Last problem. Number 14, how old is a sample? Is a sample that contains 25% of its original potassium-40 atoms. 25%. Let's take a look at potassium-40 in our table and figure out how long a half-life is. So potassium-40 has a half-life of 1.3 billion years. Let's write that down. So the half-life, one half-life, equals 1.3 billion years. How old is the sample? If it contains 25% of the original parent isotope? Well, if we look at the problem we just did, we see 25% remains after 2 half-lives have occurred. And that's true for any sample regarding the parent isotope, or not regarding, despite whatever type of parent isotope you're dealing with. So remember, 100% decays to 50% after 1 half-life. This decays into 25% after 2 half-lives. So if 2 half-lives have occurred, because we have that 25% remaining, we need to multiply this number, 1.3 billion years, by 2 to figure out how old it is. So 1.3 billion years multiplied by 2 would be 2.6 billion years. So that should be our correct answer. Great job. I hope this video was helpful for you guys to review these types of problems. If you need any help or get stuck, always feel free to email me or reach out for help. Great job.